Okay, good afternoon everybody and welcome to the May edition of the Alarm Corp CCTV webinar. My name is Piotr Tolecki. I am the National Product Manager of CCTV at Alarm Corp, and today's topic is Optic Fiber Fundamentals and System Design. Now, we ran a webinar on this topic last year. It was a very well attended webinar, a very popular topic. So I thought it timely to do a recap because it is a topic that is still very much of interest to the security industry. Okay. First, a little bit of housekeeping. Some of you may have used the GoToWebinar before, some not, so let's just quickly go through with what you are seeing. On the right, you have this webinar menu tab. You will see your own name. Now, all of you will be muted for the duration of the webinar. Now, just to verify that you can all hear me, can I please get you all to press the raise hand button? Okay, great. I'm starting to see a few hands go up. You can put them down. Next, as I said earlier, you will all be muted for the duration of the webinar, and we will be taking questions at the end. Now, with regards to questions, you will see the questions tab. You can type in your question at any time during the webinar. Just make sure to hit the send button at the bottom so that I see it, and I will go through the questions in the order that they are received. Now, all of the questions are entirely anonymous. So with that out of the way, let's get started. Today's agenda. This webinar will cover the following: the operating principles of optic fiber systems, including single mode and multi-mode. We will look at the typical components of an optic fiber system, as well as the basics of system design. We will look at the advantages of an optic fiber system as they apply to CCTV systems, and also look at the potential problems, limitations of optical fiber systems. Okay, optic fibers transmit pulses of light, much like cables transmit electricity. However, with optic fibers, it is the principle of total internal reflection, or TIR, which is what keeps the light in the fiber. Now, total internal reflection results when a light beam hits an index boundary, such as exists between water and air, or air and plastic, or between two dissimilar materials. If the light hits that boundary at just the right angle, it is reflected back. So here we see one example of total internal reflection in nature. In this example, the fish would not be able to see the person standing on the bank because of the way the light would be reflected. Next, we see here an underwater photo, and notice that you can't actually see out of the water surface. All that you see is a reflection of the turtle. And to put that back into optic fibers and light beams, here we have the same example with a water tank, but we are now shining a beam of light. And as you can see, that the beam of light is being reflected from the water surface rather than exiting. So this is the principle of total internal reflection. Okay. It is this principle that's used with the glass or plastic inside an optic fiber. And the way optic fibers are made is that there is a difference in refractive index between the core and the cladding. So you see here again we have a plastic prism, light being shown into it, and hitting at the right angle is reflected within the plastic. It doesn't actually exit until it hits it at the right angle. Here we have a schematic representation of a cylindrical optic fiber, and as you can see that when the light beam hits at the right angle, again it propagates inside the fiber rather than being scattered out of the fiber. And this angle is known as the critical angle. And here again we see another example. If we bend the fiber, that as long as the bending is not too steep, the light beam will actually stay and propagate down the fiber. So this is the principle that keeps the light beam inside an optic fiber. Okay, let's now look at optic fiber construction. We have here a single optic fiber and a finished cable, and the image will be shown shortly. Within a single fiber we have the core and the cladding, and on top of that we have a buffer coating. The core and the cladding is the actual optic fiber itself. It is the actual core that transmits the light, and the cladding just provides mechanical and moisture protection. The core and cladding are typically glass, although for short-range plastic is used, and the buffer coating is typically plastic or some sort of elastomeric material. Now, if we look at a completed optic fiber cable, which consists of a bunch of individual optic fibers, and note here that we have an outer shell of yellow Kevlar fibers. The reason we have the Kevlar fibers in a typical cable is that because Kevlar has virtually no stretch, and the worst two things you can do to an optic fiber is either stretch it or bend it over a very tight bend, because both of those things will break the glass and thus break the optical path. And of course, on the outside of the cable, you will have rubber armoring to keep it weatherproof and nice and solid. Okay. Optic fiber fundamentals, light sources. Light sources for optic fibers are either light-emitting diode, and here we have a picture of a typical light-emitting diode, or a laser diode. The major difference between a light-emitting diode and a laser diode is that a laser diode will produce a very narrow collimated beam. Invariably, the light sources are in the near-infrared range, so they are invisible to the human eye. And the light source is monochromatic. What it means is it's a single well-defined wavelength. And an example of a monochromatic light source, here we see a green laser. Green lasers are often used for testing purposes because the beam is visible. However, in optic fibers, the beam is not visible to the naked eye. LED light sources are typically used with multi-mode fiber, whereas laser diodes are typically used with single-mode fiber. And we will explore that in the coming slides as to what the difference between those two is and why you would use a particular light source with a particular type of fiber. Okay. In a multi-mode optic fiber, the core diameter is relatively large with regards to the overall cable diameter. So here we have a schematic representation of a multi-mode fiber. Because the core is large, we have multiple beam paths or multiple modes possible. In other words, you can see the light can travel straight down the fiber, or it can reflect off the walls as it travels. Now, with a multi-mode fiber, because the core is larger, two consequences. One, we can use a light-emitting diode as the light source. Light-emitting diodes can produce quite reasonable power, and it fires a cone of light. Therefore, the alignment of the light source to the fiber is not as critical because the fiber is large and you've got a fairly big cone. Most of the light finds its way into the fiber. However, in a single-mode fiber, we have a very narrow core. That means that only a single path is possible, literally shining the beam straight down the fiber with minimal bouncing. Therefore, in single-mode fiber, we use a laser diode, which produces a very collimated beam. Now, when you use a single-mode fiber, because we have a very small core, the alignment of the beam of the light source is very critical because we need to ensure that all of the laser is fired straight into the core. So that's the difference between multi-mode and single mode. And the way the beam propagates down these two fibers actually has quite significant impacts on what you can use multi-mode and single mode for and some of the benefits and limitations. Okay. So the advantages of multi-mode fiber systems. The LED light sources are still cheaper to manufacture than laser diodes. Because we have a cone of light and a fairly large core, we need lower tolerances on the connectors to align the two together. Therefore, the lower the tolerance, the cheaper and the easier it is to manufacture the connectors. So hence, multi-mode systems have an overall lower cost. However, it's not without disadvantages. With a multi-mode system, the absolute maximum transmission distance is shorter than with single mode. With multi-mode fibers, you're typically limited from a few hundred meters to 2 or 3 kilometers. If we look at single mode systems, the biggest advantage is that you can have much longer transmission distances, typically many kilometers. And the disadvantage, unfortunately, is that we do have a higher cost. A laser light source is more expensive than an LED, and because the source fiber alignment is so critical, you need tighter tolerances on the connectors, which makes them somewhat more difficult and more expensive to manufacture. Therefore, an overall single-mode system will have a higher cost. And the drawing at the bottom of the screen gives you some idea of the relative diameter of a multi-mode core inside the fiber versus single-mode. As you can see, in a multi-mode fiber, the core diameter is 62.5 micrometers, whereas the total fiber diameter is 125 micrometers. So we can see that the core is actually half the diameter of the overall fiber. Whereas in a single-mode fiber, the core is only 9 micrometers versus an overall fiber diameter of 125 micrometers. So the core is less than 10% of the total fiber diameter. Okay. Now, optic fibers ultimately do have a limitation on how far you can transmit a signal. Just like in a normal cable, the signal in an optic fiber degrades as it travels down the fiber. And there are fundamentally 3 modes of degradation. We have absorption, dispersion, and pulse spreading. Absorption. The optical fiber glass is not 100% transparent. Think of it as like a window. If you look through a single window pane, the glass looks clear. But if you've ever seen a glass carrying truck carrying several window panes together, you'll notice that the glass looks somewhat green. So the analogy is resistance. As a light source travels down the fiber, because the material absorbs some of the light, a strong, bright pulse of light will be a much weaker, dimmer pulse when it exits the fiber. So that is the method of absorption. Now, dispersion or scattering. The glass is not 100% homogeneous. We have minor imperfections within the glass itself and on its surface. And what that does is it causes irregular random reflections, thus scattering the light out of the fiber instead of propagating the light down the fiber. So this also causes attenuation and degradation of the signal. And finally, we have pulse spread or modal dispersion. And this is more so in the case of multi-mode fibers than in single mode. Light traveling down an optical fiber can take different paths or different modes. Now, each path will have a different physical path length. Now, even though light travels at the speed of light, if you have a longer path, then the light that travels down the longer path will arrive later than the light that travels down the shortest path. So what you see here in the animation below is that when you send a pulse down a fiber, the pulse actually arrives slightly spread at the receiving end because some of the photons took longer to arrive. In effect, the light pulse widens or smears as it travels. And this is why multi-mode fibers will always have a shorter maximum transmission distance than single mode, because in a single mode fiber, you do not get the same amount of pulse spreading. Okay, here we have an example of scattering, and you can see actually there a schematic representation of the irregularities in the glass surface, that some bits of light are spread out. And you see here also in an example where we have a glowing optical fiber. In real life, you would not want this to happen, because if you can see the fiber glowing, it means that the light is being scattered out of the fiber. And finally, in the dispersion, image below, you see if you fire 2 pulses, each pulse representing a binary logic 1 and the lack of a pulse representing a binary logic 0. If you fire 2 pulses very quickly, one after another, down the fiber, because of the spreading, those pulses end up running into each other. So at the receiving end, you will get to a point where instead of seeing a 1, 0, 1, you will see 1, 1, and 1, because the pulse effectively blends into 1. So this is why ultimately there is a limit on how far you can send a signal down an optic fiber. Okay, again we see here that when you have an input pulse, as it travels down the fiber, the pulse gets weaker and adjacent pulses get smeared together. Now, having said that, remember, the transmission distance that's possible with optic fiber is significantly longer than is possible with copper. With single-mode fiber in particular, we can achieve tens or even hundreds of kilometers down a single fiber without having to repeat the signal. However, ultimately there is a limit because either the received signal is too weak or the adjacent pulses have merged and it is no longer possible to detect the individual pulses and thus decode the signal. Okay, now let's look at signal encoding and decoding. An optical fiber transmitter or receiver is often called an optic fiber modem, or OFM for short. The input signal to the OFM can be analog, for example, composite video. It could be digital, such as serial telemetry, RS-232, RS-422. It could be TCP/IP traffic, or it could even be alarm state, such as contact closure. The optic fiber modem encodes or translates the signal into a series of light pulses, and these light pulses are fired into the fiber. Now, the optical signal can be analog, such as a frequency modulated signal. This was typically used in the old generation IFS, typified by the VT/VR series, or the optical signal can be binary encoded digital, such as an 8-bit or 10-bit signal that's used in the new generation of IFS. The optic fiber receiver decodes and translates the signal back into its original source format. So it's important that we match the transmitter and the receiver. Now, digital encoding can offer better image quality in CCTV and also better data transmission because we can have error correction, which is not really possible on analog transmission. So this is the one big advantage that, for example, that the new IFS family has over the previous generations, that everything is transmitted as a digital signal. Okay, so we've now talked a little bit about the basics or fundamentals of how optic fibers work, the two types of optic fibers being multimode and single mode, and the basics of signal encoding and signal decoding. So now let's go through a checklist of how we would actually go designing an optic fiber transmission system. First of all, we have to work out what is it that we need to transmit. Video. If I'm transmitting video, do I need PTZ telemetry? And how many channels of video do I need? Do I need to transmit contact closure or alarm status, such as a tamper on an enclosure? If so, how many inputs? Do I need to transmit serial telemetry only? If that case, is it RS-232? Is it RS-422? Is it RS-485? And how many channels? Is it unidirectional? Is it bidirectional? So once we work out exactly what it is that we do need to transmit, we can then go on to the next step, which is how far do I need to transmit? A few hundred meters, a few kilometers, or many kilometers? And that will then pretty much tell us which types of optical fiber modems we need and also the type of fiber. Which brings us to the next question. Do we know, are we going to be using multi-mode or are we going to be using single mode? As a rule of thumb, it's pretty safe to say that if we are looking at transmitting more than 2 or 3 kilometers, the system will invariably be single mode. Up to about 2 kilometers, most systems will be multi-mode, but it pays to check. Next question, how many fibers do we have available? Do we need to transmit all of our data over a single fiber, or do we have multiple fibers possible? That will also then have a bearing on what sort of modules we can use and select for our system. Finally, mounting and enclosure considerations. Do we want a can style of enclosure, or do we want to rack mount the system? If we have a can style, remember that you will need a dedicated power outlet to provide power to the can. If we have a rack mount, then the rack provides the power via the backplane. However, if we do go rack mounting, we need to work out how many slots do I need, because on a larger system, we may need more than one rack chassis. And to give you an example, single channel, 2-channel video transmitters and receivers are typically one rack width or one rack slot wide. Once we start getting to 4-channel and 8-channel video, we might be looking at anywhere between 2 slots and 3 slots, depending on exact module. So that has a bearing. We need to count the number of slots, and then that we need, and then we can work out, do I need one rack chassis or do I need more than one rack chassis? And as with any system design, it's always a good idea to draw up a little mud map and work out exactly which bit is going to go where. Okay, let's look at a typical system component for an analog CCTV example. We have a single analog camera. We want to transmit it over optic fiber to a digital video recorder. So we take a little single channel video encoder that mates with a fiber. At the receiving end, we have a single channel or a two-channel video decoder, and the optic fiber itself provides the path. So the optic fiber transmitter encodes the analog video into light pulses, and the optic fiber receiver decodes it back into composite analog video. Now, of course, this is a very simple example for a single channel of video. We can do the same with an optic fiber network system. In this case, we have two network switches, which are separated by a further distance than what is possible with Cat6 or Cat5. So what do? Is we take an SFP or small form factor pluggable module into the IFS network switch, and that converts the signal into optic fiber pulses. We have an optic fiber as our transmission medium. We have another SFP at the other end, and the SFP then decodes the light pulses back into TCP/IP packets. Now, the SFP modules are actually transceivers, so they do simultaneous transmit and receive. And the main reason why you would use an optic fiber for your network backbone is distance. With a normal Cat5, Cat6 cable, we are limited to 100 meters total length. Obviously, if we have to go beyond 100 meters, we need to find an alternate transmission medium, and this is where optic fiber can work very, very well. But there are other advantages to optic fiber, and we will cover those shortly. Let's look at a larger system. In this case, we have multiple video inputs. We have single channel video with a PDZ camera, so we need control telemetry back. And if we see here in the first example, we have two channels of video being run over a single fiber. In the bottom example, we have a video and telemetry link running over two fibers. So this gets back to the design question we had. Do we know whether we have a single fiber or whether we have multiple fibers available? And those sorts of questions, once we have the answers, that allows us to then select the best optic fiber modules for the job. Okay. We've discussed typical system components. Now, the ones I showed you have been for either analog video transmission or network transmission, but of course the same principle could be used in the case of contact closures, as say in the example of an automated process control system where we want to transmit things like limit switches and the state of contacts on a bit of equipment somewhere, and the equipment happens to be quite far away in the field. Okay, advantages of optic fiber as far as CCTV is concerned. First of all, we know we have much longer runs possible than either with coax or UTP. We know that with RG59 coax, anything over 150 meters, the signal just degrades too much. Whereas with IP cameras, we are limited to 100 meters in total. Now, we can run analog video for longer distances over Cat5 if we use passive balance. However, even with active UTP, we still cannot go as far as we can with optic fiber. So if we need to go longer than 2,000 meters or so, optic fibers is pretty much the only choice. Next, optic fiber preserves analog video quality over longer cable runs. When compared to copper, there is virtually no signal degradation, even with the old analog type IFS transmission. And with the new digital encoded IFS, basically, if we stick within the transmission limits, there will be no degradation because the signal transmission is entirely digital. So optic fibers are very good for large sites such as airports, seaports, or traffic/freeway monitoring, or even large shopping centers. If you had to run all the cameras in, say, a shopping center like Chadstone or Southland, there is no way you could do it with copper because of the sheer size of the buildings involved and the length of runs. Next, optic fiber is immune to any interference, radio frequency or electromagnetic interference. So it's ideal for noisy sites like power generation or energy substations, factories where you may have welding machines or variable frequency drives, smelters, public transport systems which have electric trams and trains, and of course telecommunications infrastructure where you have intentional radiation of microwave or radio radiation, all of which can cause interference in normal copper cables. Finally, optic fiber is more secure. It is not possible to intercept a signal in an optic fiber or to packet sniff. So if we do have a high security site where we are concerned about somebody intercepting the signal, optic fiber is ideal. Now, if we contrast that with, say, wireless transmission, if you take a wireless point-to-point link, even if you transmit internet or Ethernet traffic with encryption, ultimately it is possible to hack any encryption. It may not be likely, but if we are in a very high security site, optic fiber would be the better choice. Next, optic fiber electrically isolates the camera from the recorders, or if you prefer, it isolates network switches from each other. So this is ideal for areas that are subject to lightning strike. If we take a typical example of, say, an airport or a jail where we have a camera mounted up high on a pole and that pole gets struck by lightning. If we have an optic fiber system, then the camera itself will be destroyed and most likely the optic fiber transmitter will be damaged as well. However, there will be no damage to the optic fiber cable. If we have a traditional wired system, the lightning strike would destroy not only the camera, but it will also travel down the coax or UTP cable. It would therefore damage the cable, and it would quite likely cause damage to the video recorder and switcher and or equipment rack. Now, getting a cherry picker to replace the camera is one thing. Getting into the server room to replace the equipment is also fairly straightforward, if expensive. But replacing the buried cable may not be physically possible or prohibitively expensive. And if we take the example of a coax cable that's buried under an airport tarmac or under a major freeway, you can appreciate how much disruption it would cause to say, we have to dig this up to replace the cable. So yes, the biggest single advantage in a CCTV system is actually the immunity to lightning strikes. Okay, we've talked about system design and we've talked about the advantages. Now let's have a look at some of the pitfalls and problems that can happen when installing or commissioning an optic fiber system. We can divide these into either system design or installation problems. If we look at system design, we can have a mismatch. We select multi-mode transmitters and receivers for use on single-mode fiber or vice versa. Mismatch where we mix incompatible multi-mode, single-mode receivers and transmitters. Mismatch where we mix receivers and transmitters designed for different wavelengths, or systems designed for, I guess, different transmission type. However, in the new IFS system, it is relatively easy to change between single-mode and multi-mode via SFP modules. Next, installation problems. Mismatch of patch cables. Let's say we have a patch cable that's multi-mode and the rest of the system is single-mode or vice versa. Physical optical fiber cable damaged by ignoring the minimum bending radius, by twisting or stretching the cable. The result is a broken optical path. Let's say the optical fiber has been installed successfully. However, after installation, we've had a bobcat or a bulldozer error, and the cable is cut. The net result is the same. We've got a broken optical path. Let's say we have detected the damaged cable and we've repaired it, and it is possible to resplice optical fiber cable. However, the resulting splice introduces too much signal loss, and the result is an insufficient signal strength for correct signal reception. So we may have had a situation where the system was perfect before the cable was damaged. After the cable was damaged, the splice has introduced too much signal loss. And finally, poor quality patch cables or dirty connectors, both of which will introduce signal loss. Okay, so let's summarize. Optic fibers work on the principle of total internal reflection to propagate light down the fiber. We have two fundamental types of fiber, single mode and multi-mode. Multi-mode systems are typically less expensive, whereas single mode systems typically cost more but permit longer transmission distances. However, both multi-mode and single mode allow significantly longer distances than is possible with copper, and that's for either video surveillance or network transmission. Optic fiber permits higher transmission speeds and bandwidth, particularly when we're talking about local area network backbones. Optic fiber systems have interference immunity. They have lightning immunity. Interference immunity is ideal for electrically noisy environments, whereas lightning immunity can significantly reduce system maintenance and repair costs. However, optic fiber systems do require a little more care during cable installation and termination, and this is particularly with the optic fiber cable. However, optic fiber systems are very fast to commission. They are literally plug and play. There are no adjustments to make. Plug in the BNC, plug in the cable, apply power, it will work. And finally, optic fiber systems can be upgraded by replacing the transmission and receiving modules without having to replace the optic fiber itself. So let's say we have an analog video system today. There is an analog camera in the field and a classical digital video recorder back at the server room, and we are transmitting the system over optic fiber. If sometime down the track we decide to upgrade the system to a megapixel IP camera, all we need to do is change the camera and change the optic fiber encoder at the transmit and at the receive end, and the system can be upgraded without having to do anything to the optic fiber itself. And that is a major advantage. Okay, just to recap, if you look at IFS network switches, they are all capable of running optic fiber uplinks, and you can see the small rectangular slots next to the main RJ45 ports. Those are the ports that are designed to take the SFP modules for optic fiber transmission. Here we have a typical selection of IFS optic fiber transmission equipment. In the upper left-hand corner we have an IFS system rack that's empty except for the power supply module, and next to it we have a fully populated rack, and below we have a typical IFS optic fiber rack mounted enclosure. So that is what would then slide into the optic fiber rack, and that enclosure you see there is a single slot width wide. In the bottom right hand corner we have a small can style enclosure which you could bolt inside a normal equipment enclosure somewhere out in the field. Okay, would you like to know more? More information including brochures and data sheets may be found at our website www.alarmcorp.com.au. If you haven't done so, we would urge you to subscribe to the Alarm Corp Pulse newsletter to receive product information automatically. You can register online, and once approved you can get full access to the e-commerce platform including customized pricing and order placement. Please feel free to contact your nearest Alarm Corp representative. Jeff Rushton in New South Wales, Diane Brazil in New South Wales, Stephen Dinger in Victoria, South Australia and Western Australia, or myself, or you have my mobile there, 0421 378 334, or feel free to drop me an email, prd@alarmcorp.com.au. Okay, if you found this webinar interesting, please be aware that we will be holding regular CCTV webinars every month, typically second or third Wednesday of each month. Topics for this year will include the iPhone as a surveillance tool, CCTV fundamentals, network video system design, and optimizing DVR configuration, to name just three. If you go to our website and click on the resources webinars link, you will find a list of webinars planned for this year, and we look forward to your participation. And with that, just to recap, this is what our website looks like, alarmcorp.com.au, and please visit it on a regular basis, because we do have regular updates of new products and various monthly specials. Okay, now over to question time, and I can see I've already got a couple of questions. So let's start going to them. The first question is, what is OM1 and OM3 types of optic fiber cable? Good question. I think OM1 was an earlier generation of cable. The OM3 is what's currently being used. OM2 fiber cable was typically the multi-mode cable, which was 62.5/125 core diameter, whereas OM3 I think is 50 micrometers core diameter, so there's a slight difference in the core diameter. As far as impact on system design, most of the IFS modules can be used with OM3, but because of the difference in core diameter, there might be slight differences in maximum transmission distance, and that would need to be checked on a case-by-case basis. Okay. We have a acknowledgement. Thank you for the informative webinar. Thank you for the kind words. Next question is, what has happened to the alarm webinars? That is a question that I will pass on to my colleague Jeff Rushton, who is the person that is organizing and holding the alarm webinars. So please recheck the website, because both the CCTV webinars and the list of alarm-related webinars are regularly updated on the website. Okay, we have a question. Is it not better to just use single-mode fiber for all applications? That is a very good question. The answer is yes, no, and maybe. Single mode will always give you longer distance, and you can use, and that in itself is a significant advantage. However, we don't always need to go such a long distance, and as I said earlier, multi-mode solutions are typically cheaper. So if we don't need to go a very long distance, we can save often significant amount of money by going single mode. Using single mode using multi-mode will be cheaper. Using single mode will not cause any problems, but it might be a case of overkill for what we need to do. But certainly if the system budget allows for it, you can use single mode fiber all the time. It all comes down to the system budget. And unfortunately, in the security industry, it is often the case that the cheapest solutions wins the day, and that is normally the advantage of multi-mode optic fiber systems. And unless we're looking at a really, really big airport or a freeway transmission solutions, there are not that many CCTV applications where you would be running more than about 2 to 3 kilometers from camera to the receiver, and for those sorts of applications you could use multi-mode. Okay, we have a question that carry on, given that single mode fiber is probably cheaper than multi-mode fiber. The fiber cable itself might be cheaper, but at present the multi-mode transmitters and receivers are still cheaper than the single mode. So when you do the overall system design, the net system design, including the transmitters and receivers and the fiber, it'll almost certainly still be cheaper with multi-mode. Okay. What do I need to pay attention to different OM1, OM2, or OM3 patch leads? There are a couple of things you will need to pay attention to. First of all is whether it is a single mode or a multi-mode patch lead. And the second thing is the type of connectors, because we have different types of connectors. We have SC and ST, and the connectors are not compatible without adapters. And of course, every time you add adapters and additional patch cables, you do introduce additional signal loss. Is it true that it is possible to burn an optical fiber transceiver using short test cables? That is a very good question. I've actually personally not heard of that happening. Most modern systems have got automatic gain control, and I would consider that very, very unlikely unless you take the example of a very, very high-powered long-haul laser diode being used with a receiver. But I will check out, and I will email the person back with a question, because that is a very, very good question. But I've not actually heard of that. Okay, next question. Is single mode fiber more expensive in terms of equipment or fiber? We at Alarm Corp, we don't actually offer the optic fiber cable itself, so it's a little bit difficult for me to answer that, but I can tell you, looking at the price list, that multi-mode transmitters and multi-mode receivers are cheaper for an equivalent multi-mode than for an equivalent single mode. And if you go from normal single mode to a very long-haul single mode, the cost increases again. So yes, in terms of transmission and receiving equipment, multi-mode is still cheaper than single mode. Can optic fiber installation be mixed between single mode and multi-mode in the one installation? Yes, you could do that. If you have a single mode fiber and a multi-mode fiber running down the same conduit, all that you would need to do is you would need to use the right module. Pick a multi-mode module for your for your multi-mode cable, and pick a single mode module for your single mode cable. But certainly, if I look at the IFS range, there aren't any modules that can simultaneously take a multi-mode fiber and a single mode fiber. So you can't mix them in a single module, but you could mix them in a system, provided you get the right modules to match. And I hope that answered that question. Okay. Do we have any more questions? If you happen to think of any more questions after the webinar, which inevitably happens, once again, please feel free to give me either a call or drop me an email. Okay, thank you very much for your attention. I hope you enjoyed this webinar.